While the world watches storms and floods unfold, something far more significant is happening in the depths of the Atlantic. The AMOC, a vast ocean current system that moves more heat than 1,000,000 power plants combined, is now at its weakest point in over 1,000 years, and Europe is beginning to feel it. The storms that battered Portugal and Spain have shifted northward, striking France, Germany, and the United Kingdom. Meanwhile, a mysterious cold patch south of Greenland continues to cool, despite global warming. That isn't normal. Fresh water from melting ice is disrupting the ocean conveyor belt that keeps Europe temperate. The AMOC has collapsed before. Around 12,500 years ago, it plunged the northern hemisphere into nearly 1,000 years of near-glacial cold. It is not collapsing tomorrow, but it is weakening, and the changing climate patterns across Europe may be the early warning sign. Another Earth system is under strain. Stay with me, because here's what no one is connecting for you. If this story makes you question what's really happening beneath the surface, make sure to like and subscribe so you don't miss what comes next as the Atlantic continues to evolve in real time. Leave a comment telling me where you're watching from, what the weather is like right now, and whether you think we're being told the full truth about what's happening in our oceans. Part 1. The Atlantic is acting like a machine breaking down. Something unusual is happening in Europe right now, and it's not what your weather forecast is telling you. For weeks, relentless storms pounded Portugal and Spain, flooding in Valencia, rivers overflowing in Lisbon, the kind of weather that feels as if the sky itself has fractured. Then almost overnight it stopped, not gradually, not predictably, but abruptly, like someone flipped a switch. The storms didn't disappear. They moved. Now France is taking the hit. Germany is experiencing weather patterns it hasn't seen in decades. The UK is bracing for systems that seem to appear from nowhere, linger far too long, and leave chaos behind. Meteorologists call it jet stream variability. They mention atmospheric rivers, blocking patterns, the usual suspects of modern weather instability. And they're not wrong. The jet stream is behaving erratically. But here's what they don't tell you, what they can't explain in a 5-day forecast. The atmosphere doesn't make these decisions alone. It reacts. It responds to something happening far below the ocean's surface. We've been taught to think of weather as something purely atmospheric. Wind, rain, temperature, pressure systems, all occurring up there in the sky, as if disconnected from the oceans below. That's not how the planet works. The atmosphere is only the visible layer, the skin of a much larger system. Beneath it, the ocean is doing something far more powerful. It moves heat, enormous amounts of heat, from the equator toward the poles, through currents that dwarf anything we see in the sky above. Think of the Atlantic Ocean not as a passive reservoir or background scenery for ships and storms, but as a thermal engine, an active machine with moving parts, conveyor belts of water that regulate temperature across an entire hemisphere. When that engine runs properly, Europe stays mild. The Gulf Stream carries warmth northward. The jet stream remains relatively stable. Winters are cold but manageable. Summers are warm but predictable. The system functions in harmony, generation after generation, so reliably that we built entire civilizations assuming it would never change. But engines don't run forever, especially when you start feeding them the wrong fuel. Right now, the Atlantic is showing signs of mechanical stress. Not catastrophic failure. Not yet, but early symptoms. The kind of mechanic would recognize instantly. Unusual noises, irregular rhythms, components that once moved in sync now grinding against one another. If this were a car, you'd take it to a garage. If it were a power plant, you'd shut it down for inspection. But it's the ocean. So we check the forecast, vaguely blame climate change, and hope things settle back to normal. They won't. What's happening in Europe right now, the abrupt shifts, the northward migrating storms, the flooding in regions not built for floods, isn't random. It isn't chaos. It's a reaction. The atmosphere is responding to a disruption in the heat transport system beneath it. And that disruption has a name. The Atlantic Meridional Overturning Circulation. You've probably heard it called the AMOC, or more simply, the Ocean Conveyor Belt. And it is slowing down. not just in computer models, not in some distant future scenario. Now, measurably, observably, the Atlantic is transporting less heat than it used to. The engine is losing power. In Europe, perched at the receiving end of that heat, is beginning to feel what happens when the flow weakens. So when you see a storm system stalled over France for days, when you read about persistent flooding in northern Spain, when meteorologists express confusion about a jet stream behaving in ways it shouldn't, remember this. Weather explanations stop at the atmosphere, but the story goes deeper, much deeper, and what's happening below the surface is beginning to express itself above it, in ways that seem random until you understand the machine underneath. What if Europe's changing weather isn't random at all? What if it's a precise mechanical response to something we've ignored simply because it happens where we cannot see? Part 2. The cold zone that shouldn't exist. There's a region of the North Atlantic, just south of Greenland, that breaks every rule of global warming. As the planet heats up, as ocean temperatures reach record highs, as the Arctic melts faster than anyone predicted, this specific patch of ocean is getting colder. Not briefly, not superficially. At depth, year after year, temperatures there decline. This isn't a minor anomaly. It isn't within normal variability. It's a cold blob stretching hundreds of kilometers, located exactly where the ocean should be warming fastest. Scientists noticed it years ago. At first, they suspected faulty data. Instruments fail. Measurements get noisy. But as new data poured in, from satellites, research vessels, autonomous floats drifting through the depths, the pattern held. The cold zone was real, and it was growing. Here's the uncomfortable part. It isn't just cold water. It's freshening water. Salinity measurements in that region have been declining for decades. The ocean there is becoming diluted, and when seawater is diluted, it becomes lighter. When it becomes lighter, it stops sinking. And when it stops sinking, the entire conveyor belt begins to falter. Here's how it works. The Atlantic conveyor doesn't run on pumps or engines. It runs on density. Warm, salty surface water flows north from the tropics. As it travels, it cools. Cold water is dense, especially when it's salty. When that water reaches the North Atlantic near Greenland and Iceland, it becomes dense enough to sink. That sinking drives the entire circulation. It pulls more warm water northward behind it, which cools and sinks in turn, creating a loop that has operated for thousands of years. Europe receives warmth. The deep ocean receives cold, dense water. The system balances itself. But density is delicate. It depends on temperature and salinity. Make the water colder, it sinks faster. Make it saltier, it sinks faster. But make it fresher, and it stops sinking altogether. Freshwater floats. Pour enough fresh water into the North Atlantic, and you disrupt the sinking process. The conveyor slows. Heat transport weakens, and you get a cold patch exactly where deep water formation is supposed to occur. This pattern was predicted decades ago, not as fringe theory, but as a direct consequence of basic ocean physics. Melt enough ice. Add enough fresh water to the North Atlantic. The circulation will weaken. Scientists wrote papers, built models, issued warnings. Then, quietly, it began to happen, but stayed outside public debate. Because it's invisible beneath the surface. Because it unfolds over years and decades, not days and weeks. And because acknowledging it means admitting something profoundly uncomfortable. We're not just warming the planet. We're disrupting the machinery that regulates it. The cold zone isn't random. It's a fingerprint, the signature of a circulation system under stress. If you wanted to design an experiment to detect AMOC weakening, this is exactly what you would look for. A cooling region in a warming ocean, declining salinity, reduced density, all occurring precisely where deep water formation should take place. Once you see the fingerprint, one question follows. What crime does it belong to? What is pouring enough fresh water into the North Atlantic to dilute the ocean and disturb a circulation regime older than human civilization? We'll get there. But first, you need to understand just how weak the Atlantic circulation has become. Because the cold zone isn't just proof of change. It's evidence of a system approaching a threshold we truly do not want it to cross. In a uniquely destabilizing way. We talked earlier about density. Freshwater doesn't just dilute the ocean, it creates a surface layer that resists mixing. Salty water below, fresher water above, and between them, a boundary that behaves like a barrier. The fresh water spreads across the surface, preventing the colder, saltier water beneath from fully interacting with the atmosphere. And if it cannot fully interact, it cannot cool enough to sink. The conveyor belt begins to cough. But this is not a linear process. You can't say, add X amount of fresh water and the AMOC weakens by Y. Ocean systems don't operate like that. They have thresholds, tipping points. You can stress a system for years, even decades, with no dramatic visible change. And then suddenly, without warning, it slips into a new state. Scientists call this a nonlinear response. That's what makes ocean circulation so dangerous to disrupt. You can push and push, and the system absorbs it. Until one day it doesn't. The sinking stops. The circulation reorganizes. And you're left with an Atlantic fundamentally different from the one you started with. That is why Greenland's meltwater isn't background noise. It's a destabilizing input. And the rate at which it's accelerating suggests we may be approaching, or perhaps have already crossed, the point where the AMOC can no longer absorb the stress without changing. Because here's the thing about feedback loops. Once they begin, they are extremely difficult to stop. A weaker circulation means less heat transport. Less heat transport means cooler surface temperatures in parts of the North Atlantic. Cooler temperatures can slow melting locally in the short term, but they also alter atmospheric connections, affecting storm tracks and the amount of heat reaching the Arctic. Meanwhile, Greenland continues melting because the atmosphere continues warming. Freshwater keeps flowing. Circulation keeps weakening. The loop continues, each cycle making reversal more difficult. This is what concerns scientists, not because they believe collapse is imminent, but because they recognize the mechanics. They've seen this pattern in ice cores, sediment records, paleoclimate archives. They know the Atlantic has done this before. They know it can shift from one stable state to another, and when it does not easily shift back. Recovery is not guaranteed. In fact, recovery can take centuries, or longer. This isn't speculative physics. It's established science. The equations are understood. Observations align with predictions. The only uncertainty is timing. How much stress can the system absorb? How much freshwater is too much? At what point does weakening become irreversible? No one knows the exact answer, but everyone agrees we're moving closer to finding out. So here's the question at the end of Act 1. What happens when a system that has operated on inertia for thousands of years loses that inertia? What happens when the engine that keeps Europe temperate begins to seize? What happens when the Atlantic, long treated as a constant, becomes a variable? The answer may already be unfolding in the weather patterns sweeping across the continent today. But to understand how serious this could become, we have to look back, far back, to the last time the Atlantic conveyor belt failed. Because it has failed before. And when it did, it changed the world. Part 6, the last time the conveyor belt broke. 12,500 years ago, the northern hemisphere was warming. The last ice age was ending. Glaciers were retreating. Forests were spreading. Early human societies were adapting to a milder climate. And then, suddenly, everything reversed. Temperatures across the North Atlantic region plunged. In some areas, the cooling occurred within mere decades. A drop of up to 10 degrees Celsius regionally. In some places, even more. Retreating ice sheets advanced again. Forests died. Ecosystems collapsed. A warming trend that had been building for thousands of years came to an abrupt halt. This period is known as the Younger Dryas, named after a small Arctic flower that suddenly reappeared in pollen records across Europe. A plant that thrives only in cold climates. And it lasted more than 1,000 years. Not a harsh winter. Not a cold decade. More than a millennium of near-glacial conditions in the middle of a warming world. Then, just as abruptly as it began, it ended. Temperatures surged upward again. Ice retreated. The planet resumed warming. What caused it? For years, scientists debated. Then the evidence converged. The trigger was fresh water. Massive quantities released into the North Atlantic when a colossal glacial lake in North America suddenly drained. Lake Agassiz, larger than all the present-day Great Lakes combined, was held back by an ice dam. When that dam failed, the lake emptied into the ocean over a span of months to a few years. Fresh water spread across the North Atlantic. Density gradients were disrupted. The AMOC shut down. Without the ocean conveyor transporting heat northward, the northern hemisphere cooled rapidly. A warming Europe was thrown back in a deep freeze. The climatic shift was so abrupt and severe that it appears unmistakably in every paleoclimate archive we possess. Ice cores, sediments, pollen records, all of it. The Younger Dryas stands as one of the most dramatic climate events in recent Earth history, precisely because it shows what happens when Atlantic circulation fails. Now, let's be clear about the differences between then and now. We are not on the brink of a Younger Dryas scale event. The circumstances are different. Lake Agassiz no longer exists. We are not emerging from an ice age. The background climate state is different. Today's freshwater input, though enormous, is not being released in a single catastrophic surge. It's a slower process, unfolding over decades rather than months. But the similarities matter, because the mechanism is the same. Freshwater disrupts density. Disrupted density weakens circulation. Weakened circulation alters climate. The physics has not changed. The Atlantic still operates under the same principles it did 12,000 years ago. And the Younger Dryas proves that this system can fail, quickly, brutally. When it did, recovery was not swift. It didn't end because humans fixed it. It ended because the freshwater input stopped and the ocean gradually restabilized. But that took over 1,000 years. 1,000 years of cold. 1,000 years of ecosystems struggling to adapt. 1,000 years during which human societies had to reorganize entirely. We do not have that kind of flexibility today. Not with the infrastructure we've built. Not with the populations we support. Not with agricultural systems calibrated to stability. Modern civilization is optimized for predictability. We build cities in floodplains, assuming floods will remain within historical limits. We grow crops in regions that have been climatically stable for generations. We design infrastructure assuming next year will resemble last year. The Younger Dryas is a reminder that this assumption is not guaranteed. Earth systems can change faster than we are prepared for. The Atlantic, vast, stable, permanent, is more fragile than we would like to believe. And here is the uncomfortable part. We are pulling the same lever. Not as violently, not as suddenly, but persistently. Year after year, we add fresh water to the North Atlantic. We warm the atmosphere. We melt ice. We disrupt density gradients. We are running an experiment that has already been run before, and we know how it ended last time. So the question is not whether the AMOC can fail. We know it can. The question is, how much stress can it endure before it does? And are we prepared to learn the answer the hard way? Part 7. Why the official timeline keeps shifting. If you follow climate science over the past decade, you may have noticed something curious about AMOC predictions. The timeline keeps moving. This isn't because the science is wrong, but because confidence thresholds are evolving. In the early 2000s, the Intergovernmental Panel on Climate Change assessed an AMOC collapse this century as very unlikely. Not impossible, but unlikely enough that it wasn't central to policy discussions. Models showed weakening, yes, but nothing catastrophic. The consensus was that we had time. Plenty of time. Then, around 2023, something changed. New papers began appearing. Not from fringe researchers, but from respected oceanographers, painting a different picture. These studies applied early warning signal theory, a mathematical framework borrowed from ecology and complex system science. The idea is simple. Before a system collapses, it begins to display statistical fingerprints. Increased variance, slower recovery after disturbances, rising autocorrelation in the data. These are signs that resilience is eroding, that the system is approaching a tipping point. When researchers applied this framework to AMOC data, they found those fingerprints. The circulation wasn't just weakening. It was showing signs consistent with approaching a critical transition. Some studies suggested collapse could occur as early as mid-century. Others were more cautious, emphasizing data limitations and the possibility that early warning signals can be noisy. So why the shift? Why did very unlikely evolve into possible within decades? It comes down to a tension between two types of evidence. On one side, you have climate models, sophisticated computer simulations that attempt to represent the entire Earth system. They are powerful tools, but they rely on parameterizations, simplifications of processes too complex to fully resolve. When it comes to the AMOC, most models are conservative. They tend to predict gradual weakening, not abrupt collapse. They are built to avoid false alarms. On the other side, you have observational data and paleoclimate evidence, real-world measurements and reconstructions that suggest the system may be more sensitive than models assume. And when those two lines of evidence diverge, the timeline becomes uncertain. Not because scientists are confused, but because the system itself may be closer to instability than we once believed. On one side, you have the observations. Real-world data from instruments like the Rapid Array, indirect records preserved in sediments and ice cores, early warning signals extracted from time series analysis. And increasingly, the observations are outpacing the models. The weakening is unfolding faster than many simulations predicted. Statistical signatures of instability are appearing earlier than expected. The real Atlantic is not behaving like the Atlantic inside the models. That creates a dilemma. Do you trust the models, grounded in physics and validated against past climate? Or do you trust the observations telling you that something is happening right now, something the models may be missing? Most scientists try to balance both. They acknowledge the limits of models, but argue we shouldn't discard them. They also recognize that the observations are troubling, while cautioning against over-interpreting noisy data. It's a reasonable position, but it leads to careful language. Phrases like, collapse is unlikely but cannot be ruled out, or the AMOC could cross a tipping point this century if emissions remain high. And that's where it becomes political, because timelines matter. If collapse is centuries away, it's a problem for future generations. If it's decades away, it's our problem. And if it has already begun, if the weakening we see now marks the start of an irreversible transition, then it's a problem we should have addressed years ago. The truth is, we don't know the exact timeline. We may not know until it's already underway. Tipping points, by their nature, are difficult to predict precisely. You can detect warning signs. You can sense that you're approaching one, but you cannot pinpoint the exact moment until after it has been crossed. And by then, it's too late to stop it. So when you see scientists revising their estimates, when timelines shift from centuries to decades, understand what's happening. It's not that the science has suddenly changed. It's that the evidence has accumulated. Observations have piled up. Early warning signals have become clearer. And the certainty that we had time has begun to erode. But here's the real question. What if we're debating the wrong outcome? What if total collapse isn't the only thing we should fear? What if an irreversible weakening, a permanent reduction in heat transport, is already enough? Because even if the AMOC doesn't completely shut down, if it stabilizes at, say, 50% of its historical strength, that's still a different climate, a different Europe, a world where the assumptions on which our civilization was built no longer hold. Part 8. The things the models don't capture. There's a quiet unease among oceanographers. It's not something often said publicly, but it surfaces in conference conversations, in emails, in the margins of papers. The models don't capture everything. Observations keep racing ahead, showing changes that weren't supposed to happen this quickly, and the simulations struggle to catch up. Take the subsurface cooling in the North Atlantic. Models predicted it eventually, but not at this speed, not with this intensity, not in this exact spatial pattern. The cold blob is stronger and more persistent than most models simulate. That suggests either the models are underestimating the response, or there's a process in the real ocean they don't fully represent. The same applies to salinity decline. Instruments are measuring freshening rates that exceed model projections for this period. Freshwater is accumulating faster, spreading farther, penetrating deeper than simulation suggested. This isn't a minor discrepancy. It's large enough to raise the question, are the models missing a feedback? A mechanism that accelerates the process once it begins? Then there's the atmospheric response. When the AMOC weakens in models, European weather shifts, but the pattern is often symmetrical, gradual, predictable. What we're seeing in reality is messy. Storms behaving erratically. Atmospheric blocking events appearing and disappearing. A jet stream that swings sharply north, then suddenly south. The atmosphere is responding, but not in the smooth, model-friendly way we expected. Part of the issue is resolution. Climate models divide the ocean into grid cells large enough to keep computations manageable. But ocean eddies, those swirling currents that mix heat and salt, are smaller than the grid. So models parameterize them, approximating their effects. And sometimes those approximations are wrong, or they miss small-scale interactions that matter. Another issue is conservative parameterization. Scientists designing models tend to err on the side of caution. They don't want to exaggerate climate impacts. So models are tuned to avoid extreme outcomes unless evidence is overwhelming. It's responsible science, but it also means models systematically underestimate rapid change. They are built to be skeptical of catastrophe. And then there are missing feedbacks, processes we suspect exist but can't yet fully quantify. Some researchers hypothesize that as the AMOC weakens, it alters marine ecosystems, affecting the carbon cycle, which feeds back into ocean chemistry and potentially circulation itself. Others point to interactions between ocean circulation and ice sheet dynamics that are not well represented in coupled models. These ideas are clearly labeled as speculative, but they're discussed because observations keep surprising us. Here's the danger of model comfort. We start believing that because a model can simulate the past, it can reliably predict the future. But models are tools. They're only as complete as the processes they include and the assumptions they make. When the real world begins doing things the models didn't anticipate, we face a choice. We can assume the observations are wrong, that instruments are imprecise, that we simply need more data. Or we can assume the models are incomplete, that we're missing something important and the system is more fragile than we thought. History suggests we should lean toward the second option. Climate science has a record of underestimating the pace of change. Arctic sea ice disappeared faster than models predicted. Ice sheets have lost mass more quickly than early projections suggested. Sea level is rising toward the high end of uncertainty ranges. Again and again, the real Earth has proven more reactive, more dynamic, more sensitive than our simulations. So when oceanographers quietly admit the models don't capture everything, when they note mismatches between observation and simulation, when they mention missing processes and uncertain feedbacks, listen carefully. What they're really saying is, we do not fully understand what's happening. And if we don't fully understand it, we cannot confidently predict where it leads. Which brings us to a broader, more unsettling question. What else aren't we measuring? What other systems are shifting in ways we haven't detected because we're not looking in the right places? Part 9. Multiple Earth systems near their limits. The AMOC isn't weakening in isolation. It's happening on a planet where multiple systems are under pressure at the same time. They may not all be directly connected, but they're all being pushed toward their limits simultaneously. That means the risk isn't just the failure of one system. It's what happens when several destabilize together. Consider the solar cycle. We're currently in solar cycle 25, which peaked in late 2023 and early 2024. Solar maximum brings increased activity, more sunspots, more solar flares, more geomagnetic storms. That's normal. The sun follows roughly 11-year cycles. What's unusual is the intensity of some recent events. In 2024, Earth experienced multiple G5 class geomagnetic storms, the highest category, producing auroras as far south as the Mediterranean and disrupting satellite communications. Solar physicists noted that Cycle 25 has been more active than initially forecast. Does this directly affect ocean circulation? No, but it influences atmospheric chemistry, radiation levels, and space weather, subtle factors layered onto an already stressed climate system. It's another variable, another source of unpredictability. Then there's the polar vortex. In recent years, the stratospheric polar vortex over the Arctic has shown unusual persistence, sometimes remaining stable when it should oscillate, collapsing when it should be strong. These disruptions send cold air surging south into North America and Europe, creating sudden cold waves during otherwise mild winters. The vortex isn't failing, but its behavior is becoming less predictable. Combined with jet stream shifts, this makes weather patterns increasingly difficult to forecast. Ocean circulation is under strain, and not just in the Atlantic. The Southern Ocean around Antarctica is changing. The Antarctic circumpolar current, the largest current on Earth, is shifting. Upwelling patterns are evolving. Heat is penetrating deeper into the Southern Ocean, reaching the base of ice shelves and accelerating melt from below. Then there's seismicity. This is more speculative, so caution is warranted. Some geophysicists have noted apparent clustering of large earthquakes in certain regions in recent years. Clustering does not mean causation. Earthquakes are driven by tectonic forces operating on timescales far longer than human activity. But it's another data point, another stressor on a planet where infrastructure is already vulnerable. Here's why this matters. Risk compounds. When multiple systems operate near their thresholds, failure in one can ripple across others, not because they're mechanically linked, but because they strain the same human systems. Agriculture depends on stable weather, predictable seasons, and consistent ocean circulation. If the jet stream shifts, the AMOC weakens, and the polar vortex destabilizes at the same time, you don't just get bad weather. You get food supply disruptions, grid failures, infrastructure strain. Modern civilization is optimized for efficiency, not resilience. We run just-in-time supply chains that collapse if shipping routes are disrupted. We grow food in narrow climate bands that fail if temperature or precipitation shifts by only a few percentage points. We build electrical grids that cannot withstand extreme weather for more than a few days. We've created a system that works beautifully when everything is stable, but becomes extraordinarily fragile when multiple stressors hit at once. That's compound risk, not the collapse of one system, but the shrinking of margins, the thinning buffer between normal function and failure. And right now, across multiple Earth systems, those margins are disappearing. So what gives first when the margins vanish? We may be about to find out. Part 10. Why no one connects these stories publicly. You've probably noticed something by now. The connections I'm drawing between ocean circulation, climate systems, and shifting weather patterns. You don't often see that synthesis in the news. You don't hear meteorologists mention AMOC weakening while reporting European floods. You don't see headlines linking Greenland melt to jet stream changes. You don't see documentaries explaining what's happening beneath the Atlantic surface. Why not? It's not a conspiracy. It's not censorship. It's something more ordinary and more understandable. The AMOC is a difficult story to tell because it offers no easy response. When a hurricane hits, the narrative is clear. Evacuate, rebuild, strengthen codes. When wildfires spread, you fight them, create fire breaks, manage forests. When a heat wave strikes, you open cooling centers, monitor the elderly, expand air conditioning. These are discrete events with discrete responses. They fit the problem-solution framework. But the AMOC? What's the response? You can't rebuild it. You can't evacuate from it. You can't manage it like a forest. The only meaningful response is to stop adding fresh water to the North Atlantic, meaning stop ice melt, meaning stop global warming, meaning transform the entire energy infrastructure of industrial civilization. That's not a story that fits into a 3-minute news segment. So journalists focus on surface symptoms, storms, floods, because they have clear narratives. The deeper system feels abstract, slow, disconnected from immediate action. Scientists face another constraint. They are acutely aware of their responsibility. If you publish a paper declaring AMOC collapse imminent and it doesn't happen, your credibility suffers. If you overstate the risk and trigger public panic, you lose trust. Science rewards caution. Language becomes nuanced. Uncertainty is emphasized. But by the time evidence becomes overwhelming, the window for early action has often passed. Governments avoid it too. AMOC weakening demands long-term planning, international cooperation, economic transformation. It's politically toxic. No elected official campaigns on restructuring society to stabilize an ocean current. It sounds abstract, alarmist, something to worry about later. And there's fear of fatalism. If you tell people a major Earth system is weakening and approaching a tipping point, with no clear way to stop it, do they mobilize? Or do they shut down? Psychological research is mixed. Some respond to existential threat with action. Others respond with denial or paralysis. No one wants to trigger mass paralysis. But here's the cost of silence: a delayed narrative. By the time the story becomes unavoidable, when the changes are so obvious that everyone must pay attention, the options will have narrowed. Early action might have stabilized the system. Late action only manages decline. We've seen this before. Climate change itself was a delayed narrative. Scientists understood it for decades before it became a public issue. Even now, public understanding lags behind scientific consensus. The same pattern is unfolding with the AMOC. The knowledge exists. The data exist. The concern exists. But the story hasn't been told in a way that penetrates public consciousness. So why tell it now? Because certainty arrives too late. Because by the time everyone agrees the AMOC is in trouble, the transition will already be underway. The early signs are here: shifting European weather patterns, the cold blob south of Greenland, circulation weakening recorded by ocean sensors. If you wait for perfect clarity, you miss the window when understanding actually matters. The Atlantic will not announce its failure with a press release. It will tip gradually, then suddenly. And by the time the tipping is undeniable, the world will have changed in ways we're not prepared for. The question is whether we begin preparing now, while options still exist, or wait until preparation becomes damage control. Part 11. Antarctic ice does not melt symmetrically. Let's turn south for a moment. The Atlantic is not the only place where invisible processes are driving visible change. Antarctica is doing something similar, and the parallel is instructive. From satellite images, the Antarctic ice sheet looks stable, vast, white, eternal. And in some ways it is. East Antarctica, the larger portion of the continent, contains enormous amounts of ice, roughly 52 million cubic kilometers, enough to raise global sea levels by about 53 meters if it all melted. Most of it isn't going anywhere quickly. Surface melt is limited. Glaciers are not dramatically surging. Temperatures remain far below freezing, even in summer. From above, everything appears fine. But beneath the surface, it's a different story. West Antarctica, the smaller but more vulnerable section, is losing. The ice is disappearing rapidly. Not because the surface is melting, though that happens too, but because the ocean is eating away at it from below. Ice shelves, those floating extensions of glaciers that act like architectural buttresses holding the ice sheet back, are thinning. Warm ocean water circulates beneath them, melting the ice from a base. This basal melting is invisible from satellites. You cannot see it from space. There is no obvious surface signature, no dramatic visual change. And yet the effects are measurable, if you know where to look and what to measure. The ice shelves weaken. Their structural integrity declines. Glaciers accelerate. And once those glaciers lose their anchors, once the ice shelves thin beyond a critical threshold, they begin to flow into the ocean faster. The Pine Island Glacier, for example, has been accelerating for decades. Its ice shelf is thinning at a rate of several meters per year. The glacier itself now flows roughly 75% faster than it did in the 1970s. The Thwaites Glacier, often called the Doomsday Glacier because of its potential to destabilize vast sections of the West Antarctic ice sheet, is in even worse condition. Its ice shelf is fracturing. Warm water is reaching the grounding line, the point where the glacier lifts off bedrock and begins to float. And once that warm water intrudes beneath the grounded ice, once it begins melting the glacier at its most vulnerable point, the retreat can become irreversible. It is a mirror system to the AMOC story. Surface appearance versus subsurface reality. The ice sheet looks stable because we are watching the wrong layer. The real change is happening below, where warm water is doing the damage. And by the time the surface shows obvious signs of collapse, when ice shelves disintegrate, when glaciers visibly surge forward, when calving events dominate headlines, the underlying structure has already been compromised. The failure has been underway for years, perhaps decades. We only see the final phase. Scientists initially missed the early stages of this process because they were focused on surface melting. Satellites measure ice sheet color, surface temperature, reflectivity. For years, those indicators suggested relative stability. The ice was not darkening dramatically. Elevation was not collapsing across the continent. Surface temperatures were concerning, but not catastrophic. It was only when researchers began deploying instruments beneath the ice shelves, lowering sensors through boreholes drilled through thousands of meters of ice, measuring temperature and salinity in the deep ocean, that they realized the scale of the unseen melting. When they finally obtained those measurements, the data was alarming. Ocean temperatures beneath certain ice shelves were several degrees above freezing. In polar oceanography, that is significant. Water does not need to be warm in the conventional sense to melt ice. It only needs to be above the local freezing point, which for pressurized seawater can be as low as -2 degrees Celsius. Water at 1 or 2 degrees Celsius, frigid by human standards, is more than sufficient to melt ice rapidly from below. And circulation patterns were delivering that water directly to the most vulnerable parts of the ice sheet. It is the same mistake we nearly made with the AMOC. If you look only at surface ocean temperatures, if you track only atmospheric weather patterns, you miss the subsurface changes that are actually driving the system. The cold blob south of Greenland, that anomalous cooling region in the North Atlantic, was not immediately visible from space. It did not show up clearly in early sea surface temperature records because the cooling signal was rooted deeper. It required deep ocean sensors, moorings equipped with thermometers and salinity instruments at multiple depths, profiles of the entire water column. Once detected, the pattern revealed a process that had been underway for years. Freshwater from Greenland had reduced density. Deep water formation had weakened. Circulation had slowed. All of it unfolding beneath the surface while we were watching something else. The asymmetric melting of Antarctica teaches us something important. Assumptions of symmetry fail. We tend to assume that global warming will warm everything uniformly, that ice will melt evenly across the continent, that changes will be gradual, predictable, proportional to the forcing. But Earth's systems do not behave that way. They have weak points. They have positive feedbacks that amplify change in some regions while damping it in others. They respond non-linearly to stress. West Antarctica is losing roughly 5 billion tons of ice per year, while parts of East Antarctica remain stable, or even gain mass in certain regions due to increased snowfall. The North Atlantic cools while the global ocean warms. Some glaciers surge while neighboring glaciers remain stable. Some ice shelves collapse while others persist. This asymmetry is not a flaw. It is a feature of complex systems under stress. They do not fail evenly. They fail at their weakest points. And those weak points are not always where simple models or surface observations would suggest. West Antarctica is vulnerable not because its ice is inherently different, but because of its geometry. Much of it rests on bedrock below sea level, sloping downward inland. That configuration makes it susceptible to a feedback known as marine ice sheet instability. Once retreat begins in such a system, once the grounding line moves into deeper water, the ice thickens at the front. Thicker ice floats more. Floating ice flows faster. Faster flow leads to further retreat, and the cycle reinforces itself. It is a runaway process. It does not require additional warming once triggered, which means monitoring must be comprehensive. We cannot rely on averages. We cannot track only global mean temperature or total ice mass. We must watch the extremes, the anomalies, the regions that do not behave as expected, because those are often the canaries in the coal mine. Those are the early warning systems. The challenge is that comprehensive monitoring is expensive and technically difficult. Deploying sensors beneath Antarctic ice shelves requires drilling through ice up to a kilometer thick. Maintaining mooring arrays in the North Atlantic requires sending ships into some of the stormiest waters on Earth to service equipment battered by currents and corroded by salt. Autonomous floats help. They are cheaper and more numerous, but they have limits. They drift with currents rather than holding fixed positions. They cannot measure everything. They struggle under sea ice and in shallow coastal zones where many of the most critical processes occur. Their batteries eventually fail, and yet the cost of not monitoring is higher. Because the next surprise, the next subsurface process we are not tracking, could already be underway, and we would not know until it was too late. The Larsen B ice shelf collapsed in 2002, disintegrating within weeks. But the thinning, fracturing, and weakening that made that collapse inevitable have been developing for years. We simply were not watching closely enough. The same could be true today. Ice shelves we assume are stable may already be thinning from below. Ocean currents we believe to be steady may already be reorganizing. Feedback loops we have not yet identified may already be activating. The lesson for Atlantic monitoring is clear. We need more sensors, not fewer. More moorings, more autonomous floats, more deep measurements, more international collaboration to share data and coordinate observations, more investment in the unglamorous maintenance of long-term monitoring networks, because those data allow us to distinguish natural variability from systematic change. They allow us to detect early warning signals before they become crises. They buy us time. Right now, we are navigating partially blind. We have enough observations to know that major changes are underway. We know the AMOC is weakening. We know West Antarctica is losing ice. We know these processes are linked to warming and carry profound consequences. But we do not have enough observation to predict exactly when thresholds will be crossed, exactly how fast changes will unfold, exactly which regions will be hit first. And that uncertainty, the gap between knowing something is happening and knowing precisely what comes next, is costly. It makes planning harder. It makes adaptation more expensive. It makes it easier for some to dismiss the risks as hypothetical. The pattern of hidden stress repeats. Whether it is ice shelves or ocean circulation, the structure is the same. Stability at the surface, failure underneath. And by the time failure becomes visible, clear in satellite imagery, undeniable to casual observers, the damage is done. The system is already reorganized into a new state. The ice shelf has collapsed. The glacier has begun irreversible retreat. The circulation has crossed its tipping point. The only way to avoid that pattern is to look beneath the surface, to measure what is actually happening, not what we assume is happening, to invest in monitoring that reveals subsurface reality even when the surface appears calm. Because the surface almost always looks fine until suddenly it does not. Part 12. The planet's heat budget is broken. Here is something that should concern you. The Earth is absorbing more energy from the sun than it is radiating back into space. This is called planetary energy imbalance. And right now, it is larger than at any time in the instrumental record. Let me explain what that means. The sun delivers a certain amount of energy to Earth every day. Some of that energy is reflected back into space by clouds, ice, and the atmosphere. The rest is absorbed by the surface and the ocean. In a stable climate, incoming energy equals outgoing energy. The planet remains in balance. But we have disrupted that balance. Greenhouse gases trap heat, preventing some outgoing infrared radiation from escaping. More energy remains in the system than leaves it. The planet accumulates heat, and that heat has to go somewhere. Most of it goes into the ocean. More than 90% of the excess heat trapped by greenhouse gases ends up in the ocean, not the atmosphere. The ocean is the planet's primary heat sink. It absorbs energy, stores it at depth, and shields the surface from warming as fast as it otherwise would. That is why surface air temperatures, alarming as they are, actually underestimate the total amount of warming occurring in the system. The real warming is happening in the ocean, and it is happening fast. Since 1970, scientists estimate that the ocean has absorbed roughly 380 zetajoules of heat. A zetajoule is 10 to the 21st power joules. So large a number, it defies intuition. Put differently, the heat absorbed by the ocean over the past 50 years is equivalent to detonating several Hiroshima-sized atomic bombs every second, continuously, for half a century. That is the scale of excess energy added to the system. And most people have no idea because it is underwater, because it does not appear in the daily weather, because sea surface temperature has warmed, yes, but not as dramatically as land. The ocean hides the heat. It buries it in the deep, and we continue our lives unaware that the planet's energy budget is fundamentally out of balance. But heat does not distribute evenly in the ocean. It concentrates in certain regions. It penetrates certain depths, and how it redistributes depends on circulation, especially currents like the AMOC. When the AMOC is strong, it transports heat northward efficiently. Warm tropical water flows toward the North Atlantic, releases heat to the atmosphere, and sinks. That process moderates surface temperatures and stores heat in the deep ocean long term. When the AMOC weakens, redistribution changes. Heat accumulates in the tropics. The North Atlantic cools at the surface, but can warm at depth. The spatial pattern of ocean heat storage shifts. And that matters, because redistribution shapes climate response more than totals alone. You can have the same total heat content in the ocean, but if it is distributed differently, the impacts are entirely different. A warm North Atlantic with a cold deep ocean produces different weather than a cool North Atlantic with warm subsurface layers. Structure matters. Configuration matters. And that structure is now changing in ways we are only beginning to measure. Tropical storms draw energy from warm surface waters. If the tropics retain more heat because the AMOC is not transporting it north, surface waters warm further, fueling stronger hurricanes, heavier rainfall, faster intensification. Meanwhile, regions that once received that transported heat, like Western Europe, experience altered patterns. Cooler surface waters in some zones. Warmer subsurface layers that interact differently with the atmosphere. The entire ocean-atmosphere relationship shifts. When you hear about record ocean temperatures, understand what it signifies. It is not just surface warmth. It is a distorted planetary heat budget. Energy is accumulating faster than it is released, and that accumulation is being redistributed by circulation systems that are themselves changing. We are adjusting the thermostat and breaking the plumbing at the same time. And that brings us to something unexpected. The machines are beginning to detect patterns in this chaos that humans cannot see. Part 13. AI is starting to detect patterns humans miss. Artificial intelligence excels at pattern recognition, sometimes better than humans. Feed it vast datasets, complex time series, millions of data points, and it identifies correlations, anomalies, structural shifts that would take human analysts years to detect. Increasingly, AI is being applied to climate data, not to replace scientists, but to assist them, to filter noise, to highlight signals worth investigating. And it is finding things. Machine learning algorithms trained on ocean temperature and salinity data have begun identifying regime shifts, moments when the statistical properties of the system change abruptly. Not gradual trends, discontinuities. The system behaves one way, and then suddenly it behaves differently. When researchers revisit those flag periods, they often find something physical, an AMOC weakening event, a shift in circulation patterns, a change in heat transport. The algorithm does not understand ocean physics. It does not know what the AMOC is. It simply detects that the statistical fingerprint has changed, and that is both powerful and unsettling, because it suggests that there may be patterns in the data we have been missing, that the ocean may be transitioning between states in ways not obvious to the naked eye. The question is not whether AI will play a role in this field. It already is. The question is how we interpret what it finds, and how early we are willing to act when the signals are statistical before they are undeniable. And that may soon become one of the most important decisions we face. One is a fusion reactor held together by gravity. The other is a fluid envelope surrounding a planet. They operate under entirely different physics, on completely different timescales, governed by different rules. And yet they share one essential feature. Both are systems that transport energy from one place to another. And both can fail. In a star, energy is generated in the core and transported outward to the surface. In smaller stars like the Sun, that transport happens through radiation and convection. Hot gas rises, cooler gas sinks. Energy moves from the interior to the exterior. It is a conveyor belt, not so different from the ocean. And as long as energy transport remains efficient, the star stays stable. The process is elegantly simple. Nuclear fusion in the core produces high-energy photons, particles of light, that begin a long journey outward. In the Sun's radiative zone, those photons bounce around, absorbed and re-emitted by atoms millions of times, taking thousands of years to travel from the core to the outer layers. Then in the convective zone, the physics shifts. The gas becomes opaque enough that radiation alone can no longer carry heat effectively. Convection takes over. Hot plasma rises toward the surface, cools, and sinks again, forming vast circulation cells that transport energy upward. This two-stage transport system keeps the Sun in balance. The energy produced in the core equals the energy radiated from the surface. The temperature gradient remains stable. The pressure gradient counteracts gravity. Everything functions, and it has functioned this way for roughly 4.5 billion years. But there are stars where this process does not unfold smoothly. Massive stars, for example, contain regions where energy transport becomes unstable, convective layers that oscillate, zones where radiation struggles to escape efficiently. Sometimes those instabilities trigger a transition. The star reorganizes how it transports energy. It shifts from one stable state to another. And sometimes that shift is not gentle. It explodes. Supernovae are the most dramatic example. A massive star exhausts its nuclear fuel. The fusion reactions that generated outward pressure suddenly stop. Gravity takes over. The core collapses in seconds, rebounding in a shockwave that tears the star apart. But before that final explosion, there are warning signs. The star becomes unstable. Its outer layers swell. It begins losing mass. Energy transport grows erratic. To a distant observer, the star may appear mostly normal, perhaps slightly brighter or dimmer than usual, but nothing obviously catastrophic until it is. I'm not suggesting that the ocean is going to explode, but the parallel is instructive because the pattern of instability is similar. A system dependent on efficient energy transport, a disruption that reduces that efficiency. A period of instability where the system struggles to maintain balance but cannot fully succeed. Then a transition, rapid or gradual, into a new state. Accretion disks around black holes show the same pattern. These are disks of gas spiraling inward, releasing energy as they fall. Energy transport in an accretion disk is governed by turbulence, magnetic fields, and viscosity. Such disks can remain stable for long periods, emitting energy steadily, but they can also become unstable. The inner disk may suddenly drain. The outer disk may brighten. The entire system can flip into a different regime. Astronomers call these state transitions, and they can happen quickly. A disk that seemed stable for years can transform in a matter of weeks. I have seen the X-ray telescope data monitoring these systems. The light curves, graphs of brightness over time, show long stretches of stable emission followed by sudden spikes or drops. The disk accretes steadily, transporting angular momentum and energy predictably. And then something changes. Perhaps the magnetic field reorganizes. Perhaps turbulence crosses a critical threshold. Perhaps temperature or density exceeds a limit. The system tips. Energy that was being radiated steadily becomes trapped, or trapped energy suddenly escapes. The entire structure reconfigures. Why does this happen? Because nonlinear systems do not decline gradually. They resist change. They absorb stress. They maintain equilibrium until they cannot. And then they transition abruptly. Before the transition, behavior appears stable. There may be fluctuations, small anomalies, hints of instability. But to an external observer, the system seems fine until suddenly it is not. That is what makes tipping points so dangerous and so difficult to predict. The system gives very little warning. It preserves the appearance of stability until the precise moment it changes state. And once the transition begins, it is often irreversible on any practical timescale. You cannot unexplode a star. You cannot rewind a state transition in an accretion disk. The new equilibrium becomes the system's reality. Returning to the old equilibrium would require conditions that no longer exist. This is a universal pattern. It appears in ecosystems, in financial markets, in climate systems. Any complex system dominated by feedback loops and governed by thresholds that, once crossed, fundamentally alter behavior. And the reason it is universal is mathematical. These systems are governed by nonlinear dynamics, and nonlinear dynamics produce tipping points. Let me make that concrete with an ecological example. Coral reefs can exist in two stable states, coral-dominated or algae-dominated. In the coral state, the reef is biodiverse, structurally complex, economically valuable. In the algae state, it becomes a slimy monoculture with minimal biodiversity. A reef can tip between these states. Overfishing removes herbivorous fish. Algae begin to grow. Corals become stressed and die. More algae grow. Positive feedback. At some point, the reef crosses a threshold and flips to the algae state. To reverse that shift, it is not enough to simply stop overfishing. You must actively remove algae, reintroduce herbivores, wait for coral larvae to settle and grow. It is possible, but far more difficult than preventing the initial tipping. Financial markets behave similarly. They can operate in a stable regime for years, prices fluctuating around fundamentals, investors behaving rationally. Then something triggers a shift. Panic selling begins. Positive feedback activates. Everyone tries to exit at once. The market crashes. The transition from stability to collapse can occur in hours. Recovery, if it comes, takes much longer. This asymmetry, rapid collapse, slow recovery, is characteristic of nonlinear systems. Earth's ocean circulation is a nonlinear system. It contains feedbacks. It contains thresholds. And it exhibits the same early warning signals that astronomers look for in accretion disks or ecologists track in ecosystems nearing collapse. Increased variance. Slower recovery after disturbances. Critical slowing down. These are not metaphors. They are mathematical signatures. And they appear across scales, from stellar evolution to ocean currents, because the deep behavior is the same. The mathematics was developed decades ago. Dynamical systems theory, bifurcation analysis, catastrophe theory. These are the tools scientists use to study tipping points. And they're the same tools whether you're analyzing stars, oceans, or ecosystems. The equations differ because the physics differs, but the structure is identical. You have a system with multiple possible equilibria. You have a control parameter, temperature, salinity, greenhouse gas concentration, that you gradually change. And as you change that parameter, you move the system closer to a bifurcation point, where one equilibrium becomes unstable and the system jumps to another. I use this parallel carefully. I'm not saying the Atlantic is a star or a black hole. I am saying that stress systems behave similarly, regardless of the specific physics. By studying failure modes in other systems, we learn something about potential failure modes in the ocean. We learn to recognize patterns. We learn to anticipate transitions. We learn to look for early warning signs. Astronomers studying accretion disks learn to watch for specific signatures before state transitions. Increasing variability in light curves, spectral shifts indicating structural reorganization, flickering on shorter timescales. These are symptoms of a system approaching instability. When they see those signatures, they know a transition may be coming, even if they cannot predict exactly when. Climatologists do the same with ocean data. They look for increased variance in AMOC strength. They measure how long the system takes to recover after disturbances, volcanic eruptions, unusually harsh winters. They analyze autocorrelation in temperature and salinity time series. These are the same mathematical tools astronomers use, applied to a completely different physical system, and they're finding the signatures. Variance is increasing. Recovery times are lengthening. Autocorrelation patterns shift in ways consistent with critical slowing down. The ocean is exhibiting the symptoms of approaching a tipping point using the same diagnostic criteria that work for accretion disks, ecosystems, and financial markets. But here's the trap. Humans are bad at recognizing these patterns. We are biased toward linear thinking. We expect change to be smooth, gradual, proportional. We see a system weakening and assume it will continue weakening at the same pace. We do not intuitively grasp tipping points. We do not expect sudden transitions, and so we are often caught off guard when they occur. This is a deep cognitive bias. Our brains evolved to understand mostly linear cause and effect. Push something harder, it moves faster. Add weight, it becomes heavier. Most systems we interact with daily respond approximately linearly. So we extrapolate that expectation to everything. We assume the future will be a linear continuation of the past. But complex systems are not linear. They contain thresholds, feedback loops, emergent behavior that defies intuition. When we apply linear thinking to nonlinear systems, we underestimate risk. We are surprised by transitions that were mathematically predictable. That is why studying other systems matters. It trains us to think differently. It reminds us that stability is not the same as resilience. A system can appear healthy until the precise moment it is not. The absence of obvious collapse does not mean collapse is not approaching. A star on the verge of supernova can appear stable. An accretion disk on the brink of transition can appear normal. A coral reef about to flip to algae dominance can appear healthy. The warning signs are there, but they are subtle. They are statistical. They reside in variance, recovery times, autocorrelation, not in the average state. The same is true for the Atlantic. The AMOC is still functioning. It still transports heat. It still maintains some version of the circulation we are accustomed to. But the warning signs are present. The weakening trend, the increased variability, the cold blob south of Greenland, the freshwater input, the early warning signals embedded in the data. If we look only at the surface, if we ask simply, is it working or not, we will miss the transition until it is already underway. That is the lesson from astronomy, from ecology, from every field that studies complex systems. Do not wait for obvious failure. Look for subtle signatures of rising instability. Take them seriously. Prepare for the possibility that a system stable today may not be stable tomorrow. Which brings us to the final synthesis, the uncomfortable conclusion tying all of this together. Part 15. The Atlantic is not broken yet. Let me be absolutely clear. The Atlantic meridional overturning circulation has not collapsed. It is still operating. It is still transporting heat. It is functioning roughly as it has for thousands of years. If you think I have said the ocean has stopped, I have not. The AMOC is weakened, measurably and significantly, but it has not disappeared. That distinction is crucial, because the space between weakening and collapse is where we are now. That is where choices still exist. That is where action still matters. But let us also be clear about what weakening means. It does not mean the current is just slightly slower. It means the system transports less heat. It means the temperature gradients shaping European weather are shifting. It means the jet stream is responding to an ocean different from the one our climate models were built around. It means the assumptions underlying our infrastructure, agriculture, and social organization are becoming outdated. Every second, the AMOC moves roughly 15 million cubic meters of water northward across the Atlantic, about 15 times the combined discharge of all the world's rivers. It carries warm tropical water north, releases that heat into the atmosphere, and returns cold, dense water southward along the ocean floor. This circulation does not just move water. It redistributes planetary energy. It is why London has roughly the same climate as Calgary despite being hundreds of miles farther north. It is why European agriculture supports hundreds of millions of people. It is why North Atlantic fisheries are among the most productive on Earth. When that circulation weakens, even by 15 or 20%, the effects cascade. The North Atlantic cools. The tropical Atlantic warms. The temperature gradient driving the mid-latitude jet stream shifts. And the jet stream, the ribbon of fast-moving air steering weather systems, begins behaving erratically. The storms sliding north from the Iberian Peninsula. The floods in regions unaccustomed to them. The unstable jet stream. These are not the final catastrophic scenario. They are not collapse. They are early mechanical failure in a system under stress. Early failures are manageable. They are uncomfortable. They are disruptive. But they are not the end of civilization. We can adapt to a weaker AMOC. We can redesign flood defenses, shift agricultural zones, update building codes, reinforce infrastructure, prepare for a less stable climate. But adaptation has limits. There's a difference between managing a weakened system and managing a collapsed one. A weakened AMOC means more extreme weather, harder to predict patterns, periodic crises. A collapsed AMOC means a fundamentally different climate, one no amount of preparation can fully offset. Regional cooling in parts of Europe of up to 10 degrees Celsius. Shifting drought belts. Reorganized monsoon systems. Agricultural zones built over millennia, becoming unviable within a generation. The window between those states is narrowing. That is why waiting for absolute certainty is so costly. By the time every scientist agrees, every model confirms, every uncertainty is resolved, it will be too late to prevent the transition. Tipping points do not wait for consensus. They do not respect political calendars or our desire for comfort before action. Once crossed, the system reorganizes around a new equilibrium, and returning to the old one, if possible at all, requires far more effort than preventing the crossing in the first place. The question is not simply whether the AMOC will collapse. It might. It might not. Timelines are debated. Thresholds uncertain. The real question is this: were we willing to risk? Modern civilization rests on assumptions of stability. We assume the climate will remain within familiar bounds. We assume the ocean will continue doing what it has always done. We assume the next decade will resemble the last. Those assumptions are embedded everywhere. Our cities, our farms, our trade routes, our insurance models, our infrastructure standards. The AMOC does not need to collapse to invalidate them. It only needs to continue weakening. Slow disasters are still disasters. They simply unfold over years instead of days. And because they do not trigger the urgency of a hurricane or an earthquake, they are harder to respond to. The evidence is accumulating. The AMOC appears weaker than at any time in at least a millennium. Greenland's ice sheet is losing mass at accelerating rates, pouring fresh water into the North Atlantic. The cold blob persists south of Greenland. Early warning signals are emerging in the data. Models may be conservative. Paleoclimate records show that the AMOC has shut down before, and when it did, it happened quickly, not over centuries but over decades. This is not a call for panic. It is a call for awareness. The weather chaos affecting Europe is not isolated. It is not random. It is connected. It is a surface expression of a deeper subsurface process we have been tracking for years. The window to stabilize the system is closing, but it is not closed. That is the message. Not inevitability, not helplessness, but urgency. The Atlantic does not need to collapse to reshape civilization. It only needs to stop behaving the way we build everything around. And that shift has already begun. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.